In this session, we'll be looking at the AQA Combined Science Trilogy paper from the year 2020, and it's the higher paper. As always, it's always good to download the paper from the description below and have a go before you go through the answers. Figure 1 shows the inside of a plug. We have the brown wire, the live pin, the earth pin, the blue wire, the green and yellow wire, and the neutral pin, and the cable. So what should be done to connect the wires in the plug correctly? So the blue wire needs to be connected to the neutral, and the green and yellow wire needs to be connected to the earth pin. A correctly wired plug and cable connects a washing machine to the mains electricity supply. Give the potential difference and the frequency of the mains electricity supply in the UK. So the potential difference in the UK should be 230 volts and the frequency is 50 hertz. The washing machine is switched on. What is the potential difference between the neutral and the earth wire? So the potential difference should be 0 volts. The plug has a fuse. Draw the circuit symbol for a fuse. So the circuit symbol is a rectangle with a straight line going through it. The washing machine has a metal case. A fault causes the live wire to make an electrical connection with the metal case of the washing machine. The earth wire is not connected to the metal case of the washing machine. Explain why it would not be safe for the person to touch the metal case. And this is because the person could get electrocuted because people have current in them, so they provide a connection to earth. The earth wire is now connected to the metal case of the washing machine. Explain why it could now be safe for a person to touch the metal case even if the wire touches the metal case. So now, because the earth wire is actually touching the metal case, there's going to be less resistance in the earth wire, so the charge will flow through the earth wire instead of the person. Different radioactive isotopes emit different types of nuclear radiation. A polonium-210 nucleus emits an alpha particle and turns it into a lead nucleus. This can be represented by the equation below. So what we've got to remember is with radioactive decay, the atomic masses and the atomic number on the reactant side is equal to the product side. So if we've got an alpha particle, we know the atomic mass is 4 and the atomic number is 2. So if we've got to work out the value of A in the equation, which is the atomic mass of the lead, it's going to be 210 take away 4, which is 206, because 206 plus 4 equals 208. Then if we look at the atomic number, we've got 84, which produces an alpha particle of atomic number 2. So 84 take away 2 is 82. And 82 plus 2 is 84, which is the atomic number of the polonium. A strontium nucleus emits a beta particle and turns it into a yttrium nucleus. This can be represented by the equation. What are the values of A and Z? So we've got to remember that the atomic mass and the atomic number of the strontium is going to be equal to the atomic mass number and the atomic number of the yttrium plus the electron. So electron has an atomic mass of 0 and it has an atomic number of -1. So 89, and we've got an electron which has a mass of 0, which means the atomic mass of the yttrium must also be 89. Now, if we look at the atomic number of strontium is 38. So we need the atomic number of yttrium. So the number take away 1 has to equal 38. So that would be 39, because 39 take away 1 is 38. So the atomic number on the strontium side and the product side is equal in each case. Gamma radiation is another type of nuclear radiation. What does gamma radiation consist of? So gamma radiation is not a particle, it is an electromagnetic wave. Explain the differences between the properties of alpha, beta and gamma radiation. Alpha radiation is the same as a helium nucleus, so it has a charge of +2. Beta radiation is an electron, so has a charge of -1, and gamma radiation is an electromagnetic wave, so has 0 charge. Alpha radiation has the largest particle size and is therefore the most ionising, the least penetrating, and travels the shortest range, which is a few centimetres in air. It's also stopped by paper. Beta is a smaller particle than alpha and is more penetrating than alpha but less than gamma. It is more ionising than gamma but less than alpha, and it is stopped by a thin sheet of aluminium. Gamma is an electromagnetic wave and is most penetrating, least ionising, travels the largest distance in air and reduced by thick lead. A student investigates how the resistance of a wire varies with length, and we've got to explain why the student needed to adjust the variable resistor each time she changed the length of the wire. And this is because by changing the variable resistor, you're changing the resistance, which means you can keep the current the same and control the temperature. The student recorded the three measurements of the potential difference, across 0.1 metre length of wire, and they calculated the mean, which is there. So we've got to calculate x. So first of all, the mean, which is 0.7, is going to be our result 1, which is x, plus our result 2, which is 0.18, plus our result 3, which is 0.15, divided by 3 because we have 3 answers. So that means that 0.17 times 3 is going to be x plus 0.18 plus 0.15. So if we calculate this part out, this first part here, 0.17 times 3 is 0.51, and that equals x. And if we add these two together, plus 0.33. So to work out x is going to be 0.51 take away 0.33. And if we calculate that out, we should get an answer of 0.18 volts. Figure 3 shows the results for 5 different lengths of a wire, and we've got to describe the relationship between the length of the wire and the resistance of the wire. So in these types of questions, you need to make sure you're looking at your headings of your axes here. So we can see that as one goes up, the other goes up. So that means that we've got a graph that is directly proportional. So we can say resistance is directly proportional to the length of wire. If you did say that the length of wire is directly proportional to the resistance, you would still get the marks. A glucometer uses the resistance of a blood sample to calculate the glucose concentration in a person's body. The glucometer applies a potential difference of 0.9 volts across the blood sample. The glucose concentration of the blood sample is 0.98 grams per litre. Determine the current in the blood sample. So we would draw a line up from 0.98, then draw a line across from where it meets the graph and read off. So reading from the graph, I would say we've got about 7.5 ohms, or anywhere in between 7.4 and 7.6 would be correct. So the graph shows that the resistance is 7.5 ohms. We can see from my information here that the potential difference is 0.9 volts, and we are going to try and work out the current. So the equation that we are going to use is potential difference is current times resistance. If we rearrange this equation, we can see that the current is the potential difference divided by resistance, and if we put our numbers in, that is 0.9 divided by 7.5, and if we calculate that out, the current will be 0.12 amps. A new tube is used each time the blood sample is tested. Explain why valid results are only obtained if identical tubes are used. So we only want the glucose concentration to affect the resistance, so the volume should be kept the same by using identical tubes. Figure 5 shows a wood-fired hot tub. What type of fuel is wood? So wood is a renewable biofuel. Now give 2 environmental effects of using wood as an energy resource. So if we're burning wood, it can cause smoke and air pollution. We can say that cutting down trees can lead to deforestation or destruction of habitat. So any one of those would be right. So first of all, as we're burning the wood, the chemical store of the energy of the wood is going to decrease. Now, that energy is going to be transferred to the internal or the thermal energy of the pipes. So the internal energy of the pipes is going to increase. And then that internal energy from the pipes is also going to increase the internal energy of the water as it heats it up. So as we said, as the wood burns, chemical energy store decreases, the internal energy store of the metal pipes increase, which then in turn increase the internal energy store of the water. Now the temperature of the water reaches 42 degrees Celsius. The temperature then stays constant even though the fire continues to burn. Explain why the temperature of the water stays constant. So here, when the wood is heating the pipes and then the water, the amount of energy that is being transferred to the surroundings from the water is the same as the amount of energy that is being transferred to the water. Ice cream is made by cooling a mixture of liquid ingredients until they freeze. Which statement describes the motion of particles in solid ice cream? So if it's a solid, the particles will be vibrating about a fixed position. How is kinetic energy and potential energy of the particles change? So how does the kinetic energy and the potential energy of particles change as a liquid is cooled and frozen? So when a liquid is cooled, the kinetic energy is going to decrease, so it has to be one of these two. And if the kinetic energy decreases, there is less potential energy, which decreases, so the answer is this one here. Figure 6 shows a bowl used for making ice cream. The walls of the bowl contain a liquid coolant. The bowl is cooled to minus 20 degrees Celsius before the mixture is put into the bowl. The bowl causes the mixture to cool down and freeze. So we've got to explain why the different thermal conductivities of the metal and the plastic are important in the design of the bowl. So first of all, if we're looking at the metal, this metal here needs to have high thermal conductivity because we want the energy to be transferred at a high rate from the ice cream to the liquid coolant in order for it to freeze and cool down. Secondly, we want this plastic surface here to have low thermal conductivity because we don't want heat from the surroundings to be entering into the liquid coolant because we want the liquid coolant to stay at minus 20 degrees Celsius. The liquid coolant has a freezing point below minus 20 degrees. Explain one other property that the liquid coolant should have. Now, if it's being a coolant, the liquid coolant needs to have a high specific heat capacity. The reason for this is it will be able to absorb large amounts of energy with not having a large temperature change. The initial temperature of the mixture is 20 degrees Celsius and the mixture freezes at 1.5 degrees Celsius. So this question is in relation to this diagram here where we have a mixture which needs to cool in order for it to solidify and become ice cream. So the total amount of internal energy that's transferred from the mixture to the coolant for it to freeze is 165,000 joules of internal energy. The specific heat capacity of the mixture is 3,500 joules per kilogram per degree Celsius. The specific latent heat of fusion of the mixture is 255,000 joules per kilogram, and we've got to calculate the mass and give our answer to two significant figures. First of all, the energy needed for the mixture to change from 20 degrees Celsius to minus 1.5 degrees Celsius for it to solidify is worked out using this equation here. So energy is mass times specific heat capacity times the change in temperature. So mass times specific heat capacity times the change in temperature. So the energy is the mass we don't know, specific heat capacity we know is 3,500, and the change of temperature has gone down by 21.5 degrees Celsius. So the energy, if we calculate out those numbers there, is going to be 75,250 times the mass. Now, the second part to this energy transfer is the actual amount of energy needed for it to change state from the liquid to the solid. And to work out that amount of energy, it is the mass times the latent heat. So that amount of energy is going to be the mass times the specific latent heat of fusion, which we know is 255,000 joules of energy because we were given that here. So the overall change in energy, therefore, is going to be the amount of energy that was needed for it to change temperature from 20 degrees Celsius to minus 5 degrees Celsius, and we work that out at 75,250 times the mass, plus the amount of energy that was needed for the change of state. So that was 255,000 times the mass, and that is the total internal energy that was transferred. So now, as we can see from our information provided here, the total internal energy is 165 kilojoules, which is 165,000 joules. And if we do 75,250 M plus 255,000 M, sorry, that should be 1,000 M, that gives us a total of 330,250 M being the mass. And then if we rearrange that, our mass is going to be 165,000 divided by 330,250. So the mass will calculate out at 0.499 kilograms, and to get that last mark where we have to give our answer to two significant figures, that would be because it's 499, that would be 0.50 kilograms. A student modelled radioactive decay by rolling some dice in a tray. The dice that had landed on the number 6 were removed from the tray, and the removed dice represented the nuclei that had decayed. Why is rolling a dice suitable model for radioactive decay? And that's because it's a random process, which is the same as radioactive decay. Now, the student rolled 144 dice and removed all those that landed on the number 6. The student rolled the remaining dice again and removed all those that landed on the number 6. When the student had rolled the dice 20 times, there was 9 dice left. Calculate the most likely number of times the student had rolled the dice before the number of dice had halved. I need to show you working out. So 144 to half is 72. So if we think about this, if you have 144 dice, the probability of it not landing on a 6, so the ones that are remaining, is going to be 5 out of 6. So we've got to calculate how many times we get that probability of 5 out of 6, which are not the number 6, until we get closest to 172. So 144 times 5/6, 120. So then 120 times 5/6, 100. And then 100 times 5/6 is going to be 83.3. So we're getting close now. So 83.3 times 5/6, 69.4. So that is pretty close, because if we do 5/6 again, we're going to get 57, which is not as close. So the probability, so the amount of times that he would roll the dice, so we've got 1, 2, 3, 4. So we're looking at 4 rolls of the dice. So in this question, we are comparing 2 die. The first one has 8 sides and the second one has 6 sides, as in the previous question. So the half-life represented by rolling 8-sided dice is likely to be different from the half-life represented by rolling a 6-sided dice. Explain how. So the 8-sided die has a 1 in 8 chance of decay, whereas the 6-sided dice has a 1 in 6 chance of decay. So what we would say therefore is that the 8-sided dice has a smaller chance of decay, therefore it will have a longer half-life. A teacher has 2 radioactive sources, A and B. Source A has a longer half-life than B. What can be deduced about the nuclei of source A compared to source B? Do not refer, so that's important, do not refer to isotopes in your answer. So A has a longer half-life than B, so that means A has a more stable nuclei than source B, because it's not decaying as much or as quickly. Kangaroos are large animals that travel by jumping. Figure 8 shows a kangaroo. Each leg of the kangaroo has a tendon connected to a muscle. Each tendon can be modelled as a spring. When a jumping kangaroo lands on the ground, the tendons stretch. Figure 9 shows a sketch graph of how a maximum tendon length of the kangaroo during a jump changes with the speed. So explain why a kangaroo can jump higher as the speed increases. So what we can say here is that as the speed increases, the tendons are stretching much more. And if the tendons are stretching much more, there's more elastic potential energy. And if there's more elastic potential energy, that's going to be transferred into gravitational potential energy. A kangaroo has maximum gravitational potential energy of 770 joules. When the kangaroo lands on the ground, 14% of the gravitational potential energy is transferred to elastic potential energy in one tendon. The tendon has an unstretched length of 35 centimetres, and when the kangaroo lands on the ground, the tendon stretches to 42 centimetres. Calculate the spring constant of the tendon. So first of all, if we work out the energy, the elastic potential energy, it's 14% of the gravitational potential energy, which was 770. And if we calculate that out, that works out at 107.8 joules of energy. So then if we think about our equation where elastic potential energy is a half times the spring constant times the extension squared. So again, substituting our numbers in, elastic potential energy is 107.8, which equals a half times our spring constant times the extension. So we've gone from 35 centimetres to 42 centimetres. 7 centimetres is 0.07 metres. So if we do our little calculation there, that means 107.8 joules is 0.5 times 0.07 squared, which is 0.00245 times the spring constant. So the spring constant is going to be 107.8 divided by 0.00245. And if we calculate that out, we get an answer of 44,000 Newton meters as our spring constant.